You need to know the name, the equation, Olivia, the name, the equation, and the sketch. All right? So let's go through these. So these are all in your notes. The first one is the identity function. That is your line. So that looks like this. So when you sketch this for me, you are going to have a nice line diagonal right through the origin, quadrant 1 and quadrant 3. This is y equals x. So the equation is y equals x, the name is identity, and that is the picture. The next one is the squaring function. And it is the parabola. So you will memorize y equals x squared, that shape, and it's the squaring function. So if you walk in tomorrow and I say, okay, draw me a picture of the squaring function, you will do this. Okay? Yeah.
What was the first one called again?
It's, the names are on here, it's called the identity function.
Oh, okay.
And it's this equation and this picture. This is the squaring function, this equation, this picture. Next we have the cubing function. And it will be x cubed. And its picture looks like this. Now be careful, make sure there's a difference between your line and your cube. They kind of have some similarities, but you definitely want to get that squiggle into your cube. So if we were to have a quiz tomorrow, and I said, which function is this? You would all say, the cubing function, y equals x cubed. Everybody with me? Yeah. All right, the next one is the reciprocal function. Its name is reciprocal, and its equation is 1 over x. That makes sense to you, right? Reciprocal, 1 over x. And its picture looks like this. It has an asymptote here and an asymptote here, and it's like a hyperbola shape.
Didn't we do that about yesterday?
We did things that looked like that yesterday, not that particular function, but yes, Moses, that kind of shape. We totally did. And we'll review that a little bit when I'm done getting the pictures up here, but I wanted to get all our pictures up. Next, we have our square root function. And it looks like this. That's our square root function, yep. You can think of the square root function if you're having a hard time with that shape. Think of a parabola opening sideways, only just don't have the bottom part. That's the shape of it. The exponential, it's y equals e to the x. You might not be real comfortable with e. I know you studied natural logarithms last year, so you're exposed to e a little bit. Don't worry, just that's the equation for now. That's the equation. And the picture looks like this. This is like an asymptote out here. This is getting closer and closer and closer. Never crosses, but as it heads out this way, it gets closer and closer and closer. How many of you have heard of exponential growth? Somebody will say it grows exponentially. That means it grows really, really, really fast. That's exponential. It shoots up really fast. Now we have our logarithmic function. Your equation is ln x. And your picture looks like this. This is an asymptote. We're getting closer and closer and closer as we go down, but never touch it. This is your logarithm. Sometimes we get that one confused with this one. Do you see the difference between these two? Okay, this is your square root function. It starts at the origin. This is your logarithm function. It goes all the way down. So they're different. Now, I need you to pay attention because sine and cosine look a lot alike, and you need to keep them straight. So for both of them, I want you to label something 1 and -1 because that's how high and low they go. This is your sine curve. Notice, where did I start drawing? Right here at the origin.
We have to keep it within the 1.
Pardon me?
We have to keep it within like the 1.
Yeah, keep it within the ones, but you might, I mean, give it a little space to see it oscillating, but yes, it has to stay between the ones. Yep.
Wait, can it cross the x-axis?
It crosses the x-axis a zillion times. Yeah. As we get into our trigonometry, we will learn where it crosses the x-axis trace, but right now, just have that shape. It is important, though, that you're going through the origin. Because when we do our cosine, kids, it has exactly the same shape, but what's different about it?
It goes outside, or it doesn't start at the origin.
It doesn't start at the origin, it starts up there. So it's important that you are starting your curve in the right spot. I will mark it wrong if your sine is not going through the origin and if your cosine is not going through 1. All right, so make sure as you're studying that you're keeping those two straight. That's your sine and your cosine. And for the record, when we read this equation, I know it looks like sin, but we say sine. If you say sin x, you sound silly, people will laugh. It's sine x. Okay, is everybody caught up? Caught up? We have 3 to go. We have our absolute value function, which is one of my favorites. It is a V. Which one does this kind of look like? The parabola, the squaring function. So you're going to want to make sure when you're drawing these that your squaring function is, curvy, rounded, and your absolute value is a perfect V. To keep those two straight. The greatest integer function. This is my least favorite. INTX, the greatest integer function. It looks like this. Put a solid dot at the origin and 1 unit over, then open the circle. Then 1 above that, put a solid dot, This is the greatest integer function. It is a series of steps. They are 1 unit apart this way and 1 unit apart this way. And they're 1 unit long and 1 unit up. It's like walking up steps. I don't like it. And because I don't like it, we won't be doing a whole lot with it. Gotta know it. Gotta know the shape. Gotta know the name. Greatest integer function.
Does it go under the origin as well?
Uh-huh. Yep, it keeps going forever and ever. And the last one is your logistic function. Oh, they gave you the name, didn't they? The logistic function. And this is 1 unit up. So this is an asymptote this way, and 1 is an asymptote that way. That's your logistic function. It looks a little bit like a cube turned on its side. Remember your cube, what your cube is like?
Oh, there's a cube. Looks like me.
Oh, no, I meant a cubic, your cubic function, yeah.
So it's not the
Yeah.
cube.
Yeah. All right, get your note sheets out. We're going to do some recap from yesterday, I promise, but there's a couple things I need to get through today. Okay, so we got our sheets out. We're looking at section 1.3. I realize we may have a little bit left over to fill in. We're going to come back and recap. Do not panic. But I need you to look at section 1.3 in your on the note sheets. Number 1 says BFF sheet. We just did that. What are you responsible for knowing? Name, picture, equation. Okay? The names were already on the sheet. I gave you the equation, I gave you the picture. You're responsible for knowing those. A couple of my academic kids made flashcards. I'm recommending you make flashcards. Maybe on the front put the picture and on the back put the name and the equation or something like that. 12 flashcards. Number 2 says, look on page 113 of your book at number 19. It says, consider your BFFs and name 4 of them that are odd. Now, we need to talk about that. What does it mean to be an odd function? An odd function has symmetry about the origin. Odd origin. Oh. It has symmetry about the origin. Let me give you an example of one. It says there are 4, so we're going to have to come up with 4. We're going to draw. This, anybody remember which one that is? Which function is that? That's your identity function. Its equation is y equals x. That has symmetry about the origin. Here's what I mean. If you are reflecting across the origin, you have the same picture in quadrant 1 that you have in quadrant 2. flipping across the origin, 180 degrees. So if this is the point 1, 1, this would be the point negative 1, negative 1. That is symmetric about the origin. You have the same thing here as you have here. Now, look at your other functions. There's 4 of them. Can you find 3 more that have exactly the same picture, either in quadrant 1 and 3, or in quadrant 2 and 4? Can you see one there on your paper? Here?
The cubic function.
The cubic function, absolutely. That has symmetry about the origin. That is another odd function. The cubing function, y equals x cubed. Very good. Julian?
Absolute value.
Okay, now be careful about the absolute value. In fact, let me draw the absolute value here. The absolute value is one we're going to talk about, but it does not have symmetry across the origin. It has symmetry across the y-axis. And when you have symmetry about the y-axis, you are called even. So I'm glad you said that. But that would be your absolute value. Y equals the absolute value of x. That one would be considered even. Even is symmetry about the y-axis. So that means if you fold your paper on this axis, you get the mirror image. Even. I don't care. Can anybody think of either an even or an odd one? Lindsay? The reciprocal function is definitely odd. Very good. This is the reciprocal function. Y equals 1 over x, and it is definitely odd. Don't you have the same picture in quadrant 1 as you have in quadrant 3? Perfect. Now there's supposed to be one more. Can we find it?
The second one would be sine.
The sine function. Very nicely done, Julian, and anybody else that came up with that. If you took this and folded it across, like, think of whatever that point is, that's plus, plus, what would this one be? Minus, minus. It's exactly the same point, you've just flipped it into quadrant 3. So this is the sine function, and it is definitely odd. You are exactly right. So there are your 4 odds. Are there any other evens? The evens are the ones that just mirror image across the axis. Can you think of another one that's even? Cosine. Definitely cosine. Look, kids. Isn't cosine a mirror image? Yeah, I think there's another one. Oh, if that's your phone, turn it off. If that's your iPad, make it be quiet. The squaring function, which looks like this, that is definitely even. Trying to think, are there any others? I don't think so. I think that might be it. So we've got 3 evens and 4 odds. Now, do I expect you to memorize that? Absolutely not. I need you to know what even means. Even means symmetric about the y-axis. If you know your pictures, then you can figure that out. You don't need to memorize it. Good job. Very good job. Okay, on that same page, now we're going to do number 20. The 6 functions that are increasing on their entire domains. Now, I'm getting ready to erase this, so one more time, make sure this is written down somewhere. What does odd mean? Symmetric about the origin. What does even mean? Symmetric about the y-axis. Okay? Now, the next question says, of the 12, half of them are increasing on their entire domain. Now, I'd like you to look at your cosine function right here. Let's make sure we understand what increasing means. When I draw this picture, I start right here. Which way is my pencil going? Down. That would be called decreasing. until it gets to here, and then it becomes increasing. Now, would you agree that the cosine and sine are sometimes increasing and sometimes decreasing? Okay, so they're not part of this problem, because this problem says when you draw it, it's always increasing. So in other words, as you draw it, your pencil is always going up. So can you think of, look at your pictures, can you think of 6 that as you draw them, your pencil's always going up? Connor?
The natural logarithmic.
The natural logarithmic function, very good. As I draw this, left to right, and that's the key. We're talking about moving from left to right. Isn't my pencil always going to be going up? Yep, so that's one of them. Very good. That's your ln(x) function. Good. Can you think of another one? Lindsay?
Squaring.
Squaring or square root? When I draw the squaring function, Lindsay, look, what's happening here? Yeah, so I don't want that one. But the square root function would be one, because as I draw it, my pencil is always going up. Exponential, as you draw it, your pencil is always going up. When I draw the reciprocal function, it actually is going down. The cubing function, as we draw it, our pencil is going up the entire time. Identity, as we draw it, we're going up the entire time. And the logistic function. Yep, you got all 6 of them. Very good. Now, if somebody said to me, and I'm the teacher, remember, if somebody said to me, Lisa, name the 6 BFFs that are always increasing. That is not memorized. What do? I visualize the graphs. That's what I'd ask you to memorize, the graphs. If you can visualize the graphs, you can answer all of these questions. Okay, what's the next one I wanted you to do? 21. The 3 functions that are decreasing on the interval from -infinity to 0. Do not let that bother you, that notation. We're talking about, here's -infinity and here's 0. So in this area, this part of the graph, -infinity to 0, the negative side, our pencil goes down. So can you think of a graph, look at your pictures, that on this side of the x-axis, when I draw it, my pencil is going down? Be careful. As I'm drawing a logistic over here, my pencil's going up.
Absolute value.
Absolute value. Looky here, kids. What happens when I draw absolute value? Isn't my pencil going down? Yeah. Till it gets to here, and then it goes up. But over here, it's heading down. It's decreasing. The squaring function. Remember, Lindsay, on this side it is decreasing and then it increases. Good, there's one more. The sine is one of the tricky ones. The sine function is partially increasing and partially decreasing over here. So it's got both going on. So the sine isn't one.
Reciprocal.
The reciprocal function, very, very good. That's kind of a tricky one. But the reciprocal function. Because the reciprocal function on the left side goes down. The 3 functions with infinitely many local extrema. Anyone want to take a wild guess what extrema means? Okay, it means extreme values, which in terms of a picture might mean what? The tops and bottoms of the hills and valleys. Those are called extrema. They're maximums and minimums. Now, when I graph this, does it have a minimum? Yeah, it does, right here. There's its low point, right? But does it have infinitely many minimums? No, it has just one. Think of curves that have infinitely many high points and low points. Sine and cosine. The other one is a little bit tricky. The other one is the one I don't like. Greatest integer. Now you're saying to yourself, well, wait a minute, Mrs. Ford, what do you mean that has infinitely many high points and low points? Well, on this particular interval, if you only look at this step, that's the highest. That's it. That's as high as it goes. But if we look at this step, that's the highest. This step, that's the highest, and so on. So that curve has infinitely many maximums and minimums, high points or low points. That is very weird and odd, but it is.
So on the greatest integer one, are those like separate line segments?
Yep.
It's not all-
Yep, they are not connected, they are separate line segments. 23, the three functions with no zeros. Okay, what do we mean by zeros?
Go across the x-axis.
Oh, there should be no heads down, everybody should be alert, we're studying our BFFs, this is a big day. What are zeros again? Where it crosses the x-axis. So apparently there are three functions that do not touch the x-axis. Can you think of three of them?
Reciprocal?
Reciprocal function, perfect. I'll just redraw them. So we got the reciprocal function, that's one of them. Somebody said logistic, that's another one. So that's logistic. This is reciprocal. Somebody said exponential, there you go. There are the three functions that do not touch the x-axis.
Doesn't squaring like sometimes not touch the x-axis?
The basic squaring function does. Now, can we lift it up? We're going to do that, absolutely. But we're talking about the basic curves now. The basic curves. Yeah.
Can the cosine function, can that start at any point, or does that have to be at one?
Has to be at one. Now, if we stick other numbers into the problem, which we're going to learn how to do, that will change that. But when we're talking about our BFFs, those are the basic functions. It starts at one. All right. Number 23, or 4. The three functions whose range is all real numbers. Now, range is the y's, right? So I want you to look at your pictures and tell me which functions go all the way up, all the way down, and everything in between. The cubing function, perfect example. That range is all real numbers right there. Look at that. All the way down, all the way up, everything in between. There's two more. Be careful. Greatest integer is a very good guess, Jamal, but it has this y value and then it skips up here. This is skipped.
Okay.
You see what I mean?
Squared?
Squared, here's your squaring function.
What's the one? I did it natural log.
Straight line, be the identity.
Yes, I know.
So these two go all the way up and all the way down. Is there another one? The logarithmic function. You guys are getting the hang of this. Very good. That goes all the way up, all the way down, and everything in between. Does your sine function, does it go all the way up and all the way down? No, it's boxed in, right? Between 1 and -1. Okay, just a couple more and then we'll do something more fun.
It's like every time.
The four functions that do not have end behavior, we're not gonna do that, let's skip number 25 and 26, let's skip 25 and 26. Okay? Come on, one more section, then we'll do a little review, okay? Maybe let you come to the board and do some review. Number 3. How does the graph of each compare to the basic function? And then I've given you a grid because I want you to graph it. So if we look at A, the basic function is the square root function. This is a square root problem. So our square root function has this shape. This is the square root function. That's what this would look like. What does that minus 5 do? Does anybody remember? Jamal?
Make it move 5 to the left.
Almost. 5 to the right.
5 to the right.
It moves 5 to the right. Now, first of all, everybody gets 5 because the number's a 5. There are 2 ways that we can move things, Jamal. We can put the number outside the radical, or we can put the number inside the radical. And that's a difference. If the number is inside the problem with the x, then that means we're going to shift horizontally. If the number is outside, tacked on the end, that means we're going to shift vertically. So this would actually move me down 5. Vertical change, down 5. This moves me 5 units to the right. Okay? So when I sketch this, I'm going to do that picture, but I'm going to move it 5 units to the right. So this is the picture that you would draw for this problem. It's this shape, which you're going to memorize, just picked up and moved 5 units to the right. What do you think this would do if we had the the square root of x plus 2? What do you think that would do? 2 units to the left. What? Yes, the picture would look exactly the same, just moved over to the left. Yep. Now B. What shape am I going to start with? This is not a square root. B is not a square root. B is an absolute value. What shape is an absolute value? A V. So the normal picture, what I have memorized is that. Now I have stuck a 1 on the end of the problem. I didn't put it in here with the x. I stuck it on the end of the problem. So what did I tell you that did when you stick a number on the end of the problem? That's a vertical. Plus 1 goes up 1. So this picture looks like this. It is your V, simply picked up 1 unit. When you add or subtract numbers to your function, you move it. Austin? Hmm?
So, if that was a negative 1, would it
Or go down, no, wouldn't tip it upside down.
be
If it were a negative 1, it would just drop it down 1 unit, yep. All the pluses and minuses do is move you around. All you do is move. Yeah, Trey? Yep. 1, 2, 3, 4, 5. Yep. All right, 3 more, and then we'll stop and switch gears. What do you think happens in problem C, kids? This is our exponential, so we're going to start with that. What does that do to it?
It puts where it crosses the x-axis at 1.
it moves it up 1. See where that's hooked onto the end of the problem, just time to tacked on at the end? So we're going to take that equation, this picture, and we're going to pick it up 1. So it's going to look like, instead of having its asymptote here, its asymptote's going to be up 1, it's going to look like this. Let's understand, let's see, maybe we need to take a note, because I think I'm maybe trying to cover too fast here. Let's use, let's look at this. These are the rules. I'll just use absolute value as my example. Okay. This one right here goes left 1. This would move you left 1. This one would move you right 1. Look where the numbers are. They're in there with the x. That's left and right. Plus goes left, minus goes right. It's backwards of how you would think it would be, but it is. These are tacked on to the end. See the difference? So this would be up 1, and this would be down 1. Those are the rules.
Does that go for all of them? Or
Yeah,
just for absolute
yeah, no,
value?
that's for all of them. I just used absolute value because it was an easy one to write. But that's for every function. Those are the rules. So when I look at D, problem D, notice where is the addition? It's inside with the x, right? And it's an addition. So it's like this one right here. So what's going to happen to this picture? It's going to go left 1. What shape is this picture? It's a parabola. So it's a parabola sitting left 1. How do we know it's a parabola? This is a squaring function. And then E, last one. This is going to be another parabola, isn't it? But where's it positioned? Well, watch it. Be careful. Where's that 1? Is that 1 hooked up to the x like this? Or is that 1 just tacked on the end of the problem? It's tacked on to the end of the problem. So you have x squared and then minus 1. So that goes down 1. Now the parabola still looks identical. It's just moved down 1. Now, does anybody have a question about something from yesterday?